Okay, great. Hi, everyone. I'd like to thank the organizers for the opportunity to tell you about our efforts in the last few years to find relativistic stellar explosions using optical time domain surveys and to highlight the role that Gemini rapid TOO spectroscopy has played in our program. So I'll start by providing some very broad context. We have this traditional textbook story that the fate of a star depends primarily on its mass. The story goes that massive stars end their lives by developing an iron core. This collapses and neutrino irradiation causes the star to explode as a supernova, which has a characteristic kinetic energy release and ejective velocity. The mass also determines the nature of the corpse, the compact object remnant. But recent developments, particularly in observations of the explosions themselves, which I'll generically refer to as transients, are forcing us to confront the fact that the story needs to be rewritten. That the fate of a star depends obviously not just on its mass, but also on a host of parameters and processes that we really don't understand very well. Supernovae themselves can have a huge range of kinetic energies and ejective velocities. There are growing observational hints that a significant fraction of stars shed a significant fraction of their mass shortly prior to core collapse, and we'd like to know why that is. We'd like to know what parameters determine whether a star will explode at all, whether it will collapse directly and form a black hole, or whether it will explode completely, leaving behind nothing at all. And we'd like to know the relative contribution of different mechanisms for causing the explosion. There's not just neutrino irradiation. There can also be fusion, or what's called a central engine. That means tapping into the rotational spin-down power of a newborn neutron star, or the accretion power onto a newly formed black hole. And finally, we'd like to know why some massive stars do weird things, such as make gamma ray bursts. And answering that ultimately comes back to the basics of stellar evolution. So that brings me to the focus of my talk, which are extreme endpoints of massive star evolution. By far, the most famous example are long-duration gamma ray bursts. We've heard a bit about short-duration GRBs, which are thought to come from compact object mergers, but long-duration GRBs are thought to come from the deaths of massive stars. So in the traditional GRB model, the core of the star collapses and forms a compact object. Accretion or rotation powers a relativistic outflow that tunnels through the star, breaks out from the surface as a jet, and escapes into interstellar space. The jet collides with ambient gas and dust, and this produces synchrotron radiation, which we call the afterglow. We can observe the afterglow all across the electromagnetic spectrum, from X-rays to radio waves, and we can detect it out to large angles away from the jet axis. But it's thought that in order to detect the prompt burst of gamma rays itself, the GRB, we have to be looking directly down the barrel of this quite narrow, few degree wide jet. Now, GRBs, as I've just described them, are a very well-established phenomenon. They were first discovered half a century ago, and thousands have been discovered since then by satellites such as Swift and Fermi. But these satellites aren't so good at pinpointing the location of the burst. For that, you need to follow up and detect the afterglow counterpart. And today, that stage is also very routine, thanks in particular to Swift. By measuring the afterglow, you can measure the redshift to the event. We detect these all the way out to the other end of the universe. And you can also study the properties of the environments in which they explode. And at this point, there's a general consensus that long GRBs have a preference for low mass and low metallicity environments. However, there's a long-standing problem in this field that GRB satellites cannot solve, and that is that the exclusive selection of relativistic explosions via gamma rays imposes a very strong selection bias. There are a lot of reasons to think that the observed GRBs are just the tip of the iceberg, and that actually most relativistic explosions are faint in gamma rays and so are missed by GRB satellites. So here are some examples. First, off-axis GRBs must exist if our basic model of GRBs as collimated explosions is correct. Second, a jet with too many baryons, which we could call a dirty fireball, would only be able to attain a moderate Lorentz factor, much lower than a classical GRB, and would therefore not produce luminous gamma rays. And third, a jet that fails to escape the star, a choked jet, would also not produce a luminous GRB. And it's very important to try to find these classes and measure their rate, because ultimately that is how we can answer important questions, such as the contribution of these systems to the heavy elements, particularly our process elements, and to what extent they play a significant role in actually causing these stars to explode as supernovae. And today, we're finally in a position to answer these questions, because within the last few years, it's become routine to discover relativistic explosions outside the gamma ray band, and that is using optical surveys instead of gamma ray satellites. So this plot shows the phase space of optical transients. The x-axis shows the transient duration, and the y-axis shows the peak luminosity. Normal supernovae are down there on the bottom right. And today I'm going to tell you about about two emerging classes, optical afterglows, which are shown at the top, and a mysterious group of objects shown in the middle, whose prototype is this transient AT2018 COW. For both of these classes, rapid TOO spectroscopy with Gemini, which we get often within just a day of the explosion, has been really critical. Okay, so before I tell you about these transient classes in more detail, I want to walk you through the discovery process. So much of the work that I've been doing is with the Zwicky Transient Facility. This is an optical time domain survey run at Palomar Observatory in Southern California. We use a set of 3 telescopes. The smallest one does the all-sky survey and is responsible for the transient discoveries. And then the bigger telescopes are used for classification and more detailed characterization. This is 1/64th of a real ZTF image. Its full field of view is 47 square degrees, shown here compared to various other optical facilities. And it's really this large field of view that makes it particularly well suited to the pursuit of these rare and fast evolving events. So in practice, on a given night, ZTF takes images as part of several different surveys down to a certain limiting magnitude. We're currently doing the entire night sky every 2 nights in 2 different filters, and about 10% of the sky multiple times per night. The process of finding transients is fully automated. ZTF takes a new image, subtracts an image of what the sky normally looks like at that location, and every 5 sigma change results in an alert, which is just a packet of code, and we're using the same format that's going to be used by Rubin. This is very fast. So from the close of the shutter following an image to the availability of alerts for that image is just about 8 minutes. Okay, so to make this more concrete, I want to walk you through the alerts from one particularly interesting night in the history of ZTF. On this night, there were about 181,000 alerts. This might sound like a lot, but actually on a really good night, it'll be about 500,000 alerts. These come from about 150,000 unique sources. Applying some basic cuts, I'd estimate that about 76,000 of these are sort of truly astrophysical. And then we typically require that each source have 2 or more detections separated by a minimum baseline of 30 minutes. And that's important to get rid of moving objects such as asteroids. Then zooming in on those, we typically apply some cuts to try to remove as many stellar flares as possible, even though, of course, those are also scientifically interesting in their own right. And then we focus our attention on the newest events. And so by young here, I mean that the transient was detected for the first time this night with a non-detection or upper limit the previous night. And this is a very manageable number for humans to investigate. And on this particular night, there was one transient that looked like an excellent candidate for being an afterglow. So here's the subtraction. There's no known counterpart, optical counterpart at that position, down to a very faint limiting magnitude, which is what you expect for these sort of cosmological events that are occurring in sort of low mass dwarf galaxies. And indeed, this turned out to be what looked very much like an optical GRB afterglow at a redshift of 1.063, except that it had no associated detected GRB. Its nature as a relativistic explosion was really established first by Gemini. We got a spectrum with Gemini South a little under a day after the ZTF discovery through our rapid TOO program, and measured the redshift by identifying a set of absorption features in the spectrum, which I'm zooming in on in the figure. And I just want to emphasize that these observations are highly time sensitive. This transient was 19th magnitude at discovery, and every night after that, it faded by about 1 magnitude per night. So now that I've walked you through a sort of concrete example of how this works, I'll just highlight some of the results from this program from the last few years. ZTF has found 11 afterglows in the last few years. The figure on the right shows their optical light curves with time and days on the x-axis and magnitude on the y-axis. The shaded region in the background is a compilation of afterglows that were found in targeted follow-up observations of Swift GRBs. And then I'm overplotting just a subset of the individual ZTF events. So you can see these are extremely fast events. To my knowledge, these ZTF afterglows are the fastest optical transients to be discovered first in the optical band. And their discovery represents significant progress. So prior to ZTF, only one afterglow had been found with an optical survey and successfully followed up to get a redshift measurement. But with ZTF, we now have 8, of which half had redshifts measured through Gemini TOO observations. This really represents the first afterglow sample that was selected outside the gamma ray band. And so it's surprising, or at least surprising to me, that of the 11, 7 turned out to have a detected GRB counterpart. And what this suggests is that these optical searches we've been doing are finding, at least for now, a very similar population to gamma ray searches. And it also implies that at least sort of fully successful relativistic jets are actually intrinsically quite rare. In addition to afterglows, so it's very exciting to find afterglows, but that is a population that we knew existed and expected to find. There have also been new and unexpected classes of relativistic explosions that have emerged in the last few years. So AT2018 COW, or the COW, was an optical transient discovered by the ATLAS survey in 2018. At 60 megaparsecs, it was by far the nearest example of a mysterious class of objects, which are sometimes referred to in the literature as fast blue optical transients. The big surprise here was that it had radio and X-ray emission that was extremely luminous, rivaled in luminosity only really by gamma ray bursts, relativistic events. And this suggested that it too was similarly powered by compact object activity. So the plot on the right shows the radio light curve, or it's actually the millimeter light curve at 230 gigahertz. And you can see that it's orders of magnitude more luminous than that of regular supernovae and actually comparable to low luminosity gamma ray bursts. Since the discovery of 18 COW, we've been looking for additional similar events in the ZTF data. In the past, before ZTF, most of these objects were identified through archival searches, and that made it impossible to spectroscopically classify them. But today we can discover transients when they're young and follow them up before they fade away, thanks to flexible facilities like Gemini. And through this approach, we've discovered dozens of FBOTs, spectroscopically classified them, and identified 3 new transients with very luminous radio emission, very similar to 18 COW. The light curve of one of those new events, which we've nicknamed the camel, is shown here on the right. The x-axis is in days. It's along the top of the figure there. And you can see these dashed lines, which are a sort of regular supernova in the literature. And so clearly this event is, first of all, way more luminous. It's a lot faster. And it also has very blue colors at peak, which is what gives these objects their name. Now, the origin of these events is still unknown. A number of possibilities have been suggested in the literature, all of which would be extremely interesting. But I'd say we're still at this stage now when we're trying to build up a sample and measure their volumetric rate, which is a very important number for discriminating between some of these different hypotheses. So to summarize, we have sort of populations of distinct optically selected relativistic explosions that are finally within reach. This has been enabled in large part by the power of modern optical time domain surveys combined with rapid turnaround spectroscopy. ZTF's phase 2, the current phase, is scheduled to run through the end of 2023, and we're planning to make full use of this time to continue building up our sample of afterglows, particularly the ones that don't have any detected GRB counterpart, also these sort of cow-like transients, and possibly uncover new surprises. Ultimately, of course, our scientific goal is to determine the physical origin of these new classes and determine their connection to established types of supernovae. And I want to emphasize again that Gemini has been central to this effort. It's essentially unique in having this combination of this large aperture, which is important for faint events, with its rapid response capabilities, which is essential for these transients that fade within just a few days or even a few hours. And its sky coverage, ZTF routinely finds transients down to -30 degrees declination. So both Gemini North and Gemini South have been very helpful for us and for the continuous availability of the instruments. And so with that, I want to thank you for your attention and would be happy to take any questions that you have.
Okay, we'll start with questions from, okay, no questions on Slack. While we are taking questions, I would request the next speaker, one second, Gregory, to come up and get set up. Okay, Jen, go ahead.
That was a fantastic talk, Anna. Thanks very much. As Gemini director looking at this phase space, I'm just wondering how many objects are you expecting to want to follow up within this 1-day timescale once Rubin Observatory starts issuing alerts? Do you have a sense of that?
Right. So with Rubin, it will depend very strongly on what the choice of cadence ends up being. I'll say, I think the nominal Rubin survey is not ideal for these events because you really want multiple observations per night in the same filter, which is not the kind of plan for the full sky survey. So it depends very sensitively on the final survey choices. So I'm not sure I can comment so much on what the rates will be with Rubin. There are definitely plans to have surveys like ZTF also in the Southern Hemisphere, LS4, Black Gem. So they're even just with the shallow high cadence surveys, there will be a big kind of explosion in the facilities available. It won't just be the current ones. With ZTF, we trigger Gemini about probably reliably once a month. So one could imagine that it would at least be double that. So maybe something like once every week or once every couple of weeks.
Okay, thanks. Once a week sounds doable.
Any question on Slack? No? More questions from the room? All right, let's thank Anna once more.
Great, thank you.